factor. 3 terms means that it cannot be difference of squares. 3 terms means it could be a perfect square trinomial, except that these are not perfect squares. I would love to just jump into finding the multiply and add to, but because the coefficient isn't 1, I'm not looking for 2 numbers that multiply to be -5 and add to be -2. This problem is much different. So what am I looking for? Well, if we go back to how we originally multiplied binomials together, I'm looking for something that, with whatever is on the outside and the side, or the top and the side, I get a 3r squared here and a -5 here. I'm not sure what goes here, but I know that combined together they'll be -2r. So the question is, what goes here? So we can figure out what goes on the outside. I can use my multiply and add way of thinking about this, except the multiply way is a little bit different. To multiply, it's not just multiplying to be -5, it's multiplying to be this times this, -15r squared. I can't really tell you why that works. It's a nice little trick. So in these cases, when there's a number in front, you need to multiply first and last. But I know they're going to add to be the -2r. So if I look at factor pairs of -15 that add to -2r, if I cannot find them right away, I write them out. This could be negative, this could be negative, or the other way around. Which factor pair am I looking for? This one right here, 3 and -5. That means this will be 3r and this will be -5r. This is what the factor box, or the multiplying box, looks like with our correct factors on the outside. If I add up what's in here, I get what's right there. Question is, what should go on the outside? Well, if I look along the columns and the rows, all I need to find is the greatest monomial factor between the 2 in this row, the 2 in this row, and then also with the columns. So let's do that. If I look right here, both of these are -5. Right here, they both have a 3 in common and an r. Across here is just an r, and across here they have nothing in common. So I'm going to use a 1. That means, in order to get this polynomial, I needed to multiply 3r minus 5 times r plus 1. So this is the factor form. Factor. With 3 terms, the first thing I would check is for the perfect square trinomial, PST, which this is not. Neither of these are perfect squares. So I must use the multiply and add rule. But because this coefficient is not just 1, the multiply and add rule is a little bit different. I need to look for 2 numbers that multiply to be, in this case, 6x squared. Multiply the first and last. They will add up to be 5x, the middle. This is my factor box. In the factor box goes the first term and the last term. In these two go my solution to this problem over here. So, which 2 numbers multiply to be 6x squared and add to be 5x? Well, if I look at the factors of 6, it seems that 3 and 2 are the way to go. But if I look at my variables, they both need an x on the end. Now I need to fill out what goes outside of my factor box. This GCF is 2x. These are both divisible by 3. If I look across, they only have an x in common. And this one, they have nothing in common. So I put a 1. My final answer then, if I look at the top of my box and look across the bottom, it factors to this. Factor. 3 terms. This is not a perfect square trinomial since neither of these are perfect squares. So that means I need to go into my multiply or add rule. But this one, because the coefficient is not 1, I need to use the factor box. Right away I know in my factor box that the 6a squared will go up here and the minus 2 will go down there. I need to figure out which 2 terms here give me that negative 5. In order to do that, I need to find 2 numbers that multiply to be negative 12a squared, add to be negative 5a. Well, if I come over here and look at my factor pairs of 12, 6, 4, or I have the other side, 1 and negative 12, 2 and negative 6, 3 and negative 4. Any of these add to be negative 5? No. That means I cannot fill in these 2 boxes to figure out what's on the outside here. This one is prime. Factor. It's a trinomial. This is a perfect square, but this is not, so I cannot use the perfect square trinomial rule. I need to use the factor box. If I look at the leading coefficient here, it's 9. You know, I could try to reorder these and use this negative 8, but either way, I know I'm going to use the factor box. I know I'm going to need to multiply the first and last. So I know whatever terms I multiplied up here, I got a 9 on this one and a negative 8k squared on this one. Problem is, what are these 2 that they add up to be 6k? So now I need to consider what multiplies to be negative 72k squared and adds to be 6k. So I need to look at all my factors of 72. 1 and 72, 2 and 36, 3 and 24, 4 and 18, 6 and 12, 7, no, 8, no, 9 and, 8 and 9. Now I know one of these has to be negative because I'm getting a negative 72 here. So I'm going to consider the smaller one being negative because this adds to be a positive 6. Negative, 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 negative. Right here are the 2 that I'm looking for. So inside my factor box I'm going to put a negative 6k and a 12k. Now I look across the rows and the columns to fill in my factor box. Both of these have a k in common, and the greatest common factor that divides both of these is 4. Right here, these 2 both have a 3 in common. Across here, a 3, and across here they're both negative, and they're both divisible by 2 and a k. This one's a lot more complex. I'm just going to multiply back and double check my factors. 3 times 3 is 9. 3 times negative 2k is negative 6k. 3 times 4 is 12k. And 4k times negative 2k is negative 8k squared. So it looks like my factor box is correct. My factored form of this problem, 3 plus 4k, 3 minus 2k.